All right, you want to see some more homework problems? I've got some more homework problems for you. Quite a few of them, actually. We're going to start with number 8. Number 8 says, rewrite each equation in exponential form. And it says log base 16 of y equals x. Well, remember to convert between logarithmic form and exponential form. You say the base of the logarithm becomes the base of the exponential function. The input of the logarithm becomes the output of the exponential function. And the output of the logarithm becomes the input of an exponential function. The input of an exponential function, that's like the x in an exponential function, 2 to the x, 3 to the x, 4 to the x. That's what we mean by input there. And we have this nice, very colorful answer. This is exponential form, the same thing. Let's do number 20. Number 20 says, rewrite in logarithmic form. X to the negative 10/13 equals y. Again, you don't have to, but it's good practice to think about what this negative exponent means. What this really means is 1 over the 13th root of x to the 10th. The denominator of that exponent is the radical. The numerator is the exponent, and the negative means take the reciprocal. But that's not part of the problem. It doesn't want us to do anything. It doesn't want us to solve anything or simplify. It just wants us to rewrite it in logarithmic form. So the base of the exponential function is x. That becomes the base of the logarithm. Log base x. Looks pretty weird, but we do it sometimes. The input of the exponential hold on, let's color code again. The input of the exponential function becomes the output of the logarithm. The exponent is the answer to the logarithm, right? Like when we were simplifying logs, our answer, these are all exponents, right? That 18 was an exponent. Whenever we simplify logs, our answer is always an exponent, e to the exponent of 1/2. Logarithms are just exponents. Logarithms are just the inverses of exponential functions as well. Yeah, if you simplify a logarithm, you're going to get an exponent as your answer. All right, and lastly, the output of an exponential function becomes the input of the logarithm. This means the exact same thing. It's just in logarithmic form. Look at number 30. Solve for x. Log base 2 of x equals 6. Again, we're jumping ahead. Solving logarithmic equations is going to be 6.6. It's a fun section, but we're doing a little bit ahead. We're in logarithmic form here. Well, it's going to be a lot easier if we were in exponential form. So let's convert it to exponential form. Base of the logarithm, base of the exponential function. Input becomes output. Output becomes... Wait, this is literally the same problem as the notes. Well, x is 64. I'm pretty sure this is the same problem. Yeah, it's the same problem. Oh, x is 64 again. It was even better the second time. Let's do another problem. 38. 38 says, use the definition of common and natural logs to simplify. 2 times the common log of 0.0001. Remember, this 0 right here is optional. I like writing it though. Well, you could use a calculator. It's really hard to frown with a beard. You could use a calculator, or you could do this by hand. The common log is log base 10. 10 raised to what exponent is going to give us This decimal, let's convert this decimal to a fraction. This is 1/10, 1/100th, 1/1000th, 1/10,000ths. So it's x is going to be a negative number, a negative exponent, 1 divided by something, negative exponent, reciprocal, and then 10 to the first power is 10, 10 to the second power is 100, 1,000, 10,000. So this just becomes 2 times -4, and hopefully if you used a calculator, you would have also gotten -8. What would that look like? What it would look like is 2 times the common log of 0.0001. It's -8. Whoa, what a coincidence. The calculator gives you the same answer that I did. It's like I'm a calculator, except I'm a buggy calculator. I mess up things all the time. All right, let's do number 44. Evaluate the base b logarithm without a calculator. Log base 2 of 1/8 plus 4. I cannot stress enough, and especially as we get later on in this chapter, I cannot stress enough. You cannot put this in exponential form yet. Exponential and logarithmic forms only make sense when you're looking at the logarithm part by itself. Just like in number 38, we have to look at the logarithm by itself, and then we'll worry about the plus 4. So this becomes 2 raised to what power equals 1/8. Again, it's 1 divided by something. It's going to be a negative exponent. Specifically, it's going to be -3. 2 cubed is 8. We want 1/8, so add that negative in right there. We're going to give us -8 plus 4 is -4. There we go. 52. What is 52 going to look like? Okay, very similar to before, but now natural logs. The natural log of e to the -0.225 minus 3. Let's look at another way of doing this problem. I mentioned logarithms are just the inverses of exponentials. I've mentioned that quite a few times. Logarithms are just the inverses of exponentials. What do inverse functions do? Remember, back to 3.7, if we had the function composition for inverse functions, so if we had f of f inverse, right, that was f of f inverse of x, these functions, they cancel each other out completely. Well, if the logarithm is the inverse of an exponential, then as long as they have the same base, they cancel. So this just cancels 0.225 like so. This is really what's happening right here. It's kind of weird to write it like that. Mathematically, it's, shall we say, a gray area. I don't want to do that just yet, but that's basically what's happening. You get -3.225. And again, if you type this into your calculator, hopefully it would give you the same thing. The natural log of e raised to the -0.225 minus 3. Hey! Look at it right there. Last problem of this video. Shed a tear. Hopefully number 64 delivers. Real world applications. Oh yeah! I love logarithms so much. I'm curious, how can we use this in the real world? Because a ton of things are actually modeled with logarithmic functions. A lot of things have logarithmic behavior where they increase really quickly at the start, and then kind of slow down. But there's actually no asymptotes in logarithms, but we'll talk more about that in the next section. I'm getting ahead of myself. Graphs of logarithms are interesting. So let's try to parse this information. Application problems can be tough because there's a lot of information. You just kind of have to keep up. Just keep up. That's what my math professor said to me. Keep up. Great professorial advice. But it just means take your time. Don't just read through the whole thing. Read through it bit by bit and try to understand what's happening. So the exposure index, I don't know anything about cameras, by the way, so I'm kind of right there with you. I probably have a little bit more math, but the exposure index, we'll call exposure index EI. The exposure index for a camera is a measurement of the amount of light that hits the image receptor. Okay, so the EI, exposure index, is just a number that represents the amount of light that's hitting the image receptor, okay? And we can calculate this EI, this exposure index, with this equation. EI, all right, this equation is going to be important. I'm writing this down. EI equals log base 2 of f squared over t. Kind of weird to use f as a variable. Usually f is a function, but here we go. And f is known as the f-stop setting. So I guess on different cameras, they have different f-stop settings, and these f-stop settings are going to affect the exposure index logarithmically. All right, so f is the f-stop setting on the camera. I'll write that down too, right? This is exposure index. F is the f-stop setting. And then T is exposure time in seconds. So look at how I'm approaching this problem. I don't know the answer to this problem. I've not really looked much at this problem at all. I'm just approaching it the same way I want you guys to kind of approach it. Okay. So suppose the f-stop setting is 8. Ooh, okay. Suppose the f-stop setting is 8. So if f equals 8, and the desired exposure time is 2 seconds, the desired exposure time is 2 seconds. That means t is going to equal 2. What is going to be the exposure index? Okay. Find EI. This is what it's really saying. All we have to do is just plug things in. Yeah, I'm going to go down here just a little bit. So the EI, the exposure index, is the log base 2 of f, which is 8, squared, divided by t, which is 2. Well, let's just simplify this. This is log base 2 of 64 divided by 2, which is 32. Go off to the side. 2 raised to what exponent is 32? The answer is 5. So with an f-stop setting of 8, and that's what we're calling it, right? F-stop setting. Yeah, the f-stop setting is 8, and the exposure time is 2. Then the exposure index is 5. All right. Apparently the f-stop setting is how wide the lens is, kind of like the pupils in your eyes. There we go. Learned something about cameras today. There we go. That's how you approach applications. And then, yeah, you can go backwards as well, which is what you're going to do in 65. Let me know if you have questions. All right. Good luck.